So, welcome again to the new lecture of the course, properties of materials. So, let us just briefly recap what we did in the last lecture. So, in the last lecture we talked about conductivity or resistivity of metals, and we said this sigma is equal to n e square tau divided by m, where tau is relaxation time, n is number of electrons, number of conduction electrons, E is electronic charge, and m is basically mass of electron. Now, out of these for a solid you can basically vary tau effectively. Tau depends upon things like temperature. So, increasing temperature decreases tau. So, T increases, tau decreases. Defects. So, defect concentration, let us say C defect increases, tau decreases, or you can say rho, the dislocation density rho d. Rho d increases, tau decreases, and then you can have impurity. So, Ci increases, tau decreases. So, basically all of these will decrease conductivity or increase resistivity. This is what we discussed in the last lecture, and then we introduced the concept of semiconductors, and we have just said that semiconductors have forbidden energy gap in the energy band diagram, in contrast to metals. So, essentially what we said was that at lattice points in the reciprocal space, at reciprocal lattice points, electron undergoes diffraction by the lattice, causing a discontinuity in the EK diagram. So, for a single one dimensional solid, this will be something like this. So, you were initially having a plot like this. Okay. Let me just remove this line maybe. Okay, so this is E, this is K, and at the reciprocal lattice points you will have a diffraction. So, reciprocal lattice points are, so K is the reciprocal wave vector. So, it is basically a vector in the reciprocal space. Okay, so, this is plus pi by a plus 2 pi by a plus 3 pi by a and so on and so forth, minus pi by a minus 2 pi by a minus 3 pi by a. So, what happens in upon diffraction? We cannot go into details of diffraction theory, unfortunately. For this I will recommend you to go through certain books, and then it has a behavior like this. Oops. Something like that. Okay. So, you will have these discontinuities. So, these discontinuities are basically, you can say, these are the gap states. and these gaps increase in size. As you can see, the gaps increase in size. Increase in width, let us say, as one goes up in energy. So, as you increase the energy, the gaps become larger and larger. So, if this is the case, then we can say that this is essentially, we can say that energy bands are separated by an energy gap at a critical value of k. So, these are the, you can say, reciprocal lattice points, or you can say critical values of k at which lambda is equal to 2d sin theta, the Bragg's law is satisfied, leading to electron diffraction. Okay. This is what we can do essentially, and this is also direction dependent, by the way, in crystals. So, this gap is also basically, you can say, direction dependent, and crystal structure dependent, because you know the value of d depends upon the crystal structure and the type of material you have. As a result, the positions will change. So, for example, for a given crystal, let us say we have 1 0 0 direction. For 1 0 0 direction, it may be something like, if we just plot the positive part of k. So, this is E k, on this it will be minus k. So, let us just plot the one side of it. So, this diagram is something like this. Okay. So, we are not plotting the state above. So, this is in a, let us say, cubic crystal, this will be at pi by d. Okay. If you look at the same for, so this is k E, if you look at for now 110 direction, for 110 direction it may be different. For 110 the effective gap is at different. So, the reciprocal lattice point for this is at slightly higher k value, this is at root 2 pi by d, but in this case what happens is that the gap is something like, so let us say, let me just so let us say it is something like this. So, this is for 110. So, you have a certain gap state at 100 and certain gap state at 110. We can see that the effective gap, because you can see that all these things are connected in a crystal. So, the effective gap is essentially the difference between lowest point here and the above, because the crystal has gap, although at this k state, which is a larger gap, but you can see that in the crystal, while there is a gap along 110 direction, there are energy states available along 100 direction. So, basically the gap state here, if electron cannot move in this direction, it will move along in the energy states available in this direction. But between these two, there is a common area, there is a common region where the states are, there are no states in that. So, you can see that there is no state between this and that. So, for this region also there is a state available here. So, this gap will not be so this is effectively not a gap state, because although it does not, the electron will not be able to travel along 100 direction, it can switch to 110 energy states available along 110 direction. Similarly, although there is a gap in the 110 direction in this region, at this k value, electron can always shift to lower k values and travel at different energy states in 100 direction. However, having said that, this region in between is a region which is where there are no states available. So, this will be, you can say, the forbidden energy gap. So, basically no energy states are available in this region at any k value. So, this is what basically causes forbidden energy gap in semiconductors, and this forbidden gap is basically, you can say, electron cannot. So, basically you can say electrons cannot take any energy that is in the forbidden gap, because there are no states for it to reside. So, this is basically regardless of crystal direction. Okay. So, this basically is the reason for energy gap. So, there is a far more detailed physics behind it, which we do not have time to get into details of, but nevertheless basically you can say that if you have a situation when bands are, so we define these bands as the outermost energy band which is full or partially filled. This is called as, you can say, valence band. And after the forbidden gap, so and then comes a forbidden gap, and after forbidden gap there is a there are shells or bands which are empty. These are called as conduction bands. So, I mean, if you look at in a little global picture, in a global picture you may have gap states. The energy states may be like this for a given material. Let us say this is E, this is K. Okay. So, you can have energy states like this, and then you can have energy states like these, and so on and so forth. This is a hypothetical representation. So, we can see that there is a clear gap here between these 2 points, and this gap is the forbidden gap. So, this is basically, so these bands, the bands below this will be, you can say, these are valence bands, and the band above this will be the conduction band. So, these are, we are saying, partially filled or completely filled, and this will be, let us say, empty. Okay. Now, another thing is that you can see that minima in the conduction band, there is a maxima of energy states in the energy bands in the valence band. Depending upon whether these minimas are directly on top of each other or they are separate in k space, this will make a separate story. So, now I am drawing an exaggerated picture. So, if these k values are different, so this is k min, this is k max, you can see there is a separation in k space. So, when this is the case, there is energy gap here. This will make what we call as indirect band gap. I have not added the term semiconductor yet, I will come to that little later, but indirect band gap material. and if you have minima and maxima matching in the K space, so basically K min is equal to K max, then this is a direct band gap material. Okay. I will come to semiconductor and insulator a little later. So, this is the, so basically diffraction of electron from the lattice is the reason, lattice points at reciprocal lattice points is the reason you have band gap. However, a forbidden band gap will be there when electron cannot take any energy value across the K space in any direction in the crystal. If it manages to find something, then it is basically a metal. Okay. So, essentially for a metal, now let us see the difference between the two. For a metal, we see we have vacant electron energy states immediately above the highest filled level of valence band. So, this is basically the situation. You have valence band, this is the valence band. Okay. You may have forbidden gap here. So, this will be gap, let us say, but the valence band is partially filled. So, it is filled up to this point. So, you can say this is filled. So, let me just draw the boundary separately. This is valence band, this is conduction band. So, conduction band may be somewhere up. Okay. So, this is conduction band, but the valence band itself is partially empty. So, this is one representation of metal. Other representation of metal could be you have one band gap which is completely filled. So, this is valence band which is completely filled, but the conduction band may be overlapping. So, this is conduction band, this is valence band, but you have an overlap between the two. So, although, sorry, let me just draw it differently. So, you can see that this is, there is a bit of overlap. So, this is the overlap. So, it can always see the states here, available states. So, essentially in this case, electron when they acquire velocity, they move into extra available states which are empty states, or in the second case the valence band is completely full. So, this is filled valence band, but there is a overlap with the conduction band which allows the electron to go to states available in the conduction band, because there is no forbidden gap. So, here you have a gap, but valence, so gap is present, but valence band is partially empty. So, states are available for conduction. Here valence band is filled, but valence band overlaps with conduction band. So, this is what happens in this case. Now, if you now compare this with semiconductor, so basically you can say that let us first do the metals part first. So, in case of monovalent metals such as copper, silver, gold, they all of them have one electron in outermost orbital. Okay. As a result, so basically you can say that valence band is partially full. Whereas, if you look at divalent metals, such as magnesium, beryllium, etc., they have overlapping valence band and conduction conduction band. So, as a result, even if valence band is full, electron can conduct because they have empty states available in overlapping conduction band. On the other hand, if you look at trivalent metals such as aluminum, which is +3. So, in case of aluminum, the band structure is similar to monovalent metals. So, basically you can say that outermost band is partially empty. Now, in case of fourth group element, so in case of, if you look at the elements which are in so if you look at elements of fourth group elements have basically, you have in the fourth group we have, if you look at the column, okay, in the periodic table you have carbon 6 atomic number, then you have silicon which is 14, then we have germanium which is 32, then we have tin which is 50, and of course you have lead below it which is 82. So, if you look at the situation there, in this case what happens is that outermost orbital is, so you have these silicon +4, 4 plus, carbon 4 plus, and so on and so forth. So, in these cases the electronic configuration, if you look at, so this is silicon would be, since its carbon is 6, so it is 1s2, 2s2, 2p2, silicon would be 14, so this is carbon, silicon would be 1s2, 2s2, 2p6, and then 3s2, 3p2. So, this is how the electronic configuration will be. So, what basically you have here is the outermost orbitals, you can say there are even numbers. So, even numbers of electrons in the so this is same as basically similar to divalent metals. So, let us just go back for a brief second here. So, if you look at, for example, copper, the copper has a atomic number of 29 and the electronic configuration of copper is 3d10 4s1. So, you have only one electron, okay. So, which means bands are partially full. If you look at divalent, for example, magnesium has a structure of 3s2. Sorry, 3s2. So, you can see that this is an even number. Try, if you look at aluminum will be 13, which is 3s2 and 3p1. So, you can see that these are similar, but this is same. So, in this case also, in case of silicon, in case of carbon, there are even number of electrons in the outermost shell, and as a result valence band is full. But there is another difference, valence band was full in those cases as well. So, these would be, so in case of, in this case, for example, divalent metal, this would be monovalent and trivalent, okay. So, in this case, even though valence band is full, there is no overlap with the conduction band. What we have here is, this is valence band, this is completely filled. So, we are talking at 0k, of course. The conduction band, there is a gap between conduction band and valence band here. This is gap, forbidden gap, let me draw with a different line here. This is conduction band. There is a gap between these two, and this gap is basically large. So, for silicon it varies, it is about 1.1 eV. 1.1 eV is a lot of energy, because kT is equal to only 28 MeV, milli electron volt. So, you can see that this is 1100 milli electron volt. So, you will need a lot of energy in terms of thermal energy for electrons to be able to migrate. That is why silicon is also not metallic. And in case of carbon, which is diamond, this gap is nearly 5.4 eV, makes it very large. So, this makes silicon as a semiconductor, because its gap is not very large, but carbon is in the diamond form is insulator. So, this basically because the carbon is covalently bonded, sp3 hybridized and so on and so forth, because of bonding, carbon has larger gap as compared to, and we can see that. So, in the carbon case, the atoms are, the electrons, there are not too many electrons. As a result, when you come down in this case, when you come down, so you have in this case situation like this. This is the nucleus, around this you have only 6 electrons. In this case there are, so you will have 14 electrons, total of 14 electrons. So, as you come down in the column, the separation increases between the atoms. As a result, the bonding becomes weaker. So, when the bonding becomes weaker, the energy gap also comes down. So, as you go down in column, as one goes down in column, bonding weakens, and this weakens because atoms are more fartherly apart, because there are more electrons between them. So, there is a electrostatic repulsion between the electron clouds as well. So, bonding weakens, as a result the band gap goes down, and this gap is called as Eg, energy gap. So, this is forbidden gap or energy gap in metals. So, this basically is the reason why. So, essentially you can say that in case of carbon, it's, that is diamond, we saw that this gap is 5.4 eV. In case of silicon, it is 1.1 eV. In case of germanium, it goes down to 0.7 eV, germanium is even lower, and in case of tin, it goes down to 0.08 eV. So, that is why tin is basically a metal. 0.08 eV is nothing but 80 milli electron volt, whereas in this case these are all, so this is a insulator, because 5 is very large, these are semiconductors. So, basically this is where now the distinction comes. So, when the gap is, so when Eg is less than 2 to 3 eV, then the materials are called as semiconductors. When Eg is larger than 3 eV, they are called as insulators. So, basically between 2 and 3 you will call them wide band gap semiconductors, less than 2 you will call them semiconductors. So, because semiconductors, as we will see, the electron concentration, and there is a reason why we call them semiconductor, because you can make them conduct by other means. Insulators, it is very difficult to make them conduct, because their energy gap is simply too high, and semiconductors, they don't, their gap is high, but it is not high enough to make them completely insulating. We can try methods to make them conducting by various means. So, we will stop here. We have discussed in this lecture the reason of band gap, how a continuous gap is necessary across the case space to create a band gap, and then what is the reason, and the energy states below the gap are called as conduction band, and the bands below above the gap are called valence band and conduction band. So, valence band is below the energy gap and conduction band is above the energy gap. So, at 0 K for a perfect semiconductor, all the states below energy gap are filled and above is empty. We will discuss this further in the next few lectures. Thank you.